Climate change is arguably the most important issue of our time. This audience, I think, from looking at the registration, kind of reflects that. We have majors in renewable energy. We have majors in faculty from environmental science area, political science, our new minor in business environment and sustainability students are here, and insurance as well. It affects every aspect of our society, every individual, every industry. I work with the insurance industry. People may not think how climate change and insurance are related, but it's absolutely critical in looking at the risk of property, looking at how the insurance industry provides discounts for hybrid vehicles, pay-as-you-drive insurance programs, as well as what to do with the $1.8 trillion that the insurance industry invests every year. What kinds of investments should they be making if they're wanting to address climate change? So all of these aspects and all the students here in all the different areas are interested in climate change. But the kingpin for all of this is climate changing, and are humans causing that change? And so our first and our keynote presenter for today will be addressing that particular issue. So let me tell you a little bit about our keynote presenter, Dr. Wuebbles. Dr. Wuebbles is the Harry E. Pribble Professor of Atmospheric Sciences at the University of Illinois. He's a professor in the Department of Atmospheric Sciences, as well as an affiliate professor in the Departments of Civil and Environmental Engineering and in Electrical and Computing Engineering. He was the first director of the School of Earth Science and Environment at Illinois, and was the director of the Environmental Council at the university and head of the Department of Atmospheric Sciences for many years. Dr. Wuebbles is an expert in numerical modeling of atmospheric physics and chemistry. He's authored over 400 scientific articles, relating mostly to atmospheric chemistry and climate issues. He's been a lead author on a number of national and international assessments related to concerns about climate change. Dr. Wuebbles and his colleagues received the 2005 Stratospheric Ozone Protection Award from the US EPA. So he works on ozone issues as well as the climate change. And he's been honored by being selected a fellow of 3 major professional science societies: the American Association for the Advancement of Science, the American Geophysical Union, and the American Meteorological Society. He's chair of the Global Environment Change Focus Group for the American Geophysical Union, and he shares in the 2007 Nobel Peace Prize for his work with International Intergovernment Panel on Climate Change. He's also from Carlisle, Illinois here. He has 2 degrees in electrical engineering from the University of Illinois and a PhD in atmospheric sciences from the University of California, Davis. Let's introduce Dr. Wuebbles.
Thank you. Well, thank you very much for inviting me here. What I'm going to do today is tell you a little bit about the U.S. National Climate Assessment. As Jim mentioned, I'm a leader in that, and we just finished the public review of the assessment. So next week I'll start working with my team to start responding to the comments and revising the report, and that'll come out later this year. But let me tell you a little bit about that, and then what I'm going to do is, based on the National Climate Assessment plus other analyses in the peer-reviewed science literature, show you various observational data and analyses, some from climate models, that look at what we have seen and where we're heading in terms of our climate. And in the process, I hope you recognize why I start with this first slide, and which, if you get anything out of this talk, I hope you do realize that this is one of the most important issues facing humanity. The scientific evidence is clear. It shows that our climate is changing rapidly, and that human activities are the primary cause of that change. Every major science organization in the world has put out strong statements about this issue, including the U.S. National Academy of Sciences, American Geophysical Union, American Meteorological Society, and many, many other organizations. So the message I present, it's a little bit like those Verizon, when I give these kind of talks, I feel like those Verizon commercials. I haven't seen any of those recently. You know, when you pick up your phone and suddenly you've got thousands of people standing behind you. And in my case, I feel like I have the science community behind me because there is no debate in the peer-reviewed science literature. That debate is appearing in the media and on blogs and does not represent the state of the science. Now, one of the things I found out from this meeting, being asked to be here, is, based on an article I saw in the Panagraph, was that even zombies seem to be concerned about climate change. It was the first time I'd realized that. So that's kind of unique to Illinois State University. Going back to the National Climate Assessment, in 1990, Congress passed the Global Change Research Act with the idea that every 4 years, an assessment would be done, because back then it was already being recognized that this is a very important issue that we needed to be concerned about. And so Congress decided, well, every 4 years there should be a special report that looks at what's happening to our environment, what does the data tell us, what are the potential impacts of that on agriculture, on energy production, land use, water resources, et cetera, human health. And so after that was passed, it was promptly forgotten. And actually the first assessment was finally done in 2000. We did, and then it was forgotten again. We did the second one actually in 2009. It was started under President Bush's time in office. He named a small panel, including myself, to come up with a new assessment of our understanding. And we published that then in June of 2009, from the White House, actually. Well, we're now doing the third assessment. We're now trying to do this every 4 years and make this the kind of continuing process that Congress originally meant it to be. And in the process, we have a 60-member Federal Advisory Committee. We have several hundred scientists and many other types of experts, sociologists, health experts, agriculture experts, you name it, that are actually preparing the assessment itself. All of these committees represent a wide range of expertise and perspectives, not just academia and government, but also very strong representation from industry and in other organizations, non-government organizations of all types. So the assessment is quite a process. We, until last Friday, had the assessment out for public review. That's now been completed as of last Friday. And so we're waiting the comments so we can respond to those. I'm in charge of the Chapter 2, which is on the scientific basis for climate change. And then we have a series of chapters that take sectorial crosscuts and regional crosscuts to look at the potential impacts of climate change, and then finally looking at the decision-making process and what are the key issues that policymakers should be concerned about towards looking at both adaptation and mitigation. We'll say a little bit more about those things as we go through this. Now, first of all, this is global information. On the upper left-hand side are the observations that are taken from many, many thousands of observations of temperature and precipitation every day across our planet, both on land and over the oceans. And from those, we have a very good idea, particularly since about 1900, of what the temperature on our planet is doing. And we can go further back by looking at proxies, and I'll talk a little bit about that in a second. But you can see there's 3 different analyses of all those observations, one from the Hadley Center in the UK, and 2 from various science organizations in the US, the NASA Goddard Institute for Space Studies and the NOAA National Climate Data Center in Asheville, North Carolina. What all of these indicate is that we've seen about a degree and a half increase in temperature over the last century plus, and most of that change occurring in the last 50 years. And I'm really going to concentrate on that period from the last 50 years because that's where the evidence is extremely strong that those changes are occurring because of human activities. And we'll talk a little more about that later. As I said, we can go back further in time, and we can look, what the upper right-hand side shows us that using proxies like tree rings and boreholes in soils and ice cores in Antarctica and Greenland and many other sources, we can determine what the temperature was like in the past. This one just goes back 2,000 years, and basically, and the red, by the way, is the current temperature record, the one that was on the left, just replotted there. But going back 2,000 years, you can see that the current temperatures of this last decade are the highest that we have seen in those last 2,000 years. Some brand new analysis say that going back even further, we can now go back to the end of the last ice age, show that the current temperatures are higher than anything, at least going back 4,000 years and maybe further. Now, on that graph, you can also see the medieval warm period when the Vikings were in Greenland and had settlements in Greenland when it was warmer than the norm in the past. You can also see the low ice age, which affected temperatures, particularly in Europe and North America and many other parts of the world, where we had colder temperatures, and was largely due in part to changes in solar flux, but also due to a large number of volcanic eruptions that occurred during that time period and caused a cooling of the atmosphere. On the bottom indicates that there's many other indicators besides temperature that our climate is changing. The humidity is increasing just as we would expect it to. A warmer atmosphere holds more water vapor. We'll talk more about that later because that has major implications on weather. We know that well over 90% of the glaciers in the world are decreasing and decreasing rapidly. Snow cover is decreasing around the world as a whole. We're seeing the temperature increase not only over land, but also over the oceans and in the oceans as well. We're seeing a significant increase in ocean temperatures. And there's many, many other indicators that I won't have time to talk about. If we look at the global trends in temperature and put them on the map, we see that particularly we're getting the strongest warming over land, and particularly at high latitudes, but not everywhere place warms. And if you look, this is a temperature change from 1900 to 2009. But overall, the planet is warming. It's just not warming uniformly, and nor do we really expect it to if we look at the science in detail. Now, why can, might be a little backwards, and I should have shown you the forcings first, but there's various forcings on climate that can have an effect. Some of those are natural, and some of those are human. So if the solar flux changes, that certainly can have an effect on our climate, and we want to make sure we're aware of that. We've known since 1824, paper by Joseph Fourier. Anybody who's got a mathematical or engineering background would know that he's the guy who developed the Fourier transform and the Fourier series, a very famous mathematician slash scientist. Well, Fourier discovered this idea called the greenhouse effect, whereas there's certain gases in the atmosphere. Basically, the solar radiation penetrates to the Earth's, largely penetrates the Earth's atmosphere. Some is reflected back through the Earth's albedo, the most reflective things being clouds and ice. But most of that radiation is absorbed at the Earth's surface, and it's re-radiated in the infrared. So the solar radiation is mostly in visible and ultraviolet wavelengths, and then it re-radiates that radiation in the infrared. Some gases absorb infrared radiation, gases like water vapor and carbon dioxide and methane and ozone and some others. Those gases essentially will absorb that radiation emitted from the Earth's surface, re-radiate that radiation, some of it going to space, and some of it staying within the Earth system. Essentially, the greenhouse effect is like putting a blanket over the Earth and helps keep the Earth warm, and thus we have life as we know it. Without it, this would be a frozen planet. Now, what we're doing is adding more carbon dioxide, more methane, more nitrous oxide, other gases to the atmosphere, and those gases act like another blanket. You know, it's adding more to the blanket. And so the net effect is the Earth has to warm. This is the underlying basic physics of why the climate is changing. And it's not the sun, because solar flux has actually decreased over the last 4 sunspot cycles. Well, there's many natural drivers of climate. We know every 100,000 years, over the last several million years now, that the Earth's orbit around the sun starts a change in our climate system, causing what is called an ice age. And part of that, actually, part of an ice age is actually also due to responses in the carbon dioxide. So the greenhouse effect also plays a role in that, because changes the beginning of the ice formation actually affects the life on Earth in ways that affects the carbon cycle and thus affects the amount of CO2 in the atmosphere. Well, I've already mentioned the importance of the sun. I've also mentioned the importance of volcanic eruptions. Particularly, volcanic eruptions put sulfur, explosive eruptions put sulfur into the stratosphere, where that sulfur turns into sulfuric aerosols, which we can reflect sunlight, and that causes a cooling effect. That effect is now well known. We saw it particularly after the last major eruption, which was in the Pinatubo eruption in 1991. Well, we also now know that humans can have an effect on climate. This has actually been known for well over a century. First paper on it was Arrhenius, a very famous chemist who also won the Nobel Prize in chemistry, who noted that an increase in carbon dioxide could lead to significant effects on climate back in 1896. Well, at that time, we didn't actually know that carbon dioxide was increasing. And actually, an Illinois graduate, I'm proud to say, since I'm also an Illinois graduate, Charles David Keeling developed the first instrument that was able to accurately measure carbon dioxide well enough that we could determine that, in fact, there was a trend. And that instrument was put in place in 1957. We can go back further than that by using ice core analysis, which I won't go into. But we now know that he saw very rapidly within a few years that the amount of carbon dioxide in the atmosphere. If you look closely at the graph in the upper right, you see the annual cycle of carbon dioxide, which is the breathing of the biosphere. You know, in the summer, leaves are out, the CO2 is being brought in to the biosphere, and in the winter, when the leaves die off, that CO2 goes back into the atmosphere. So you see an annual cycle, but on top of that, there's a very strong increase in CO2 that can only be explained by human activities, particularly the burning of fossil fuels, but also land use change. Well, in addition to carbon dioxide, there's several other important gases that are also increasing, and I won't go into details in those, but we also know there are particles in the atmosphere. The sulfate particles, like I mentioned before, which also are increasing because of human activities, particularly the burning of coal, but also black carbon, nitrate particles, and a number of other types of particles. And those particles, some can cause a cooling effect and some can cause a warming effect, and we need to account for those in any kind of analysis we do of the climate system. We have very strong evidence that the climate change that we've seen in the last 50 years is occurring primarily is primarily human-induced. Right-hand side of that, by the way, just shows the solar cycle, 11-year solar cycle, and the net flux over the last 3 cycles, showing that it's actually been a slight decrease in the amount of radiation from the sun, which should have caused a cooling, not a warming. So we use what's called fingerprint analysis to then look at what's happening based on observations in the climate system to try to say, well, what's causing those changes? And there's a whole variety of different changes, and I won't have time to go into many of those types of analyses, but I'll just show you one. In particular, if we do an analysis with a climate model and say, well, how well can we explain that past period of change? Now, you notice that there's strong up and down variations in the climate, or in the temperature. Climate is the long-term variations in temperature, so you have to go average over 20, 30 years. And when you do that, you would expect that if you use a model that represents the climate system, it should kind of average over a lot of those year-to-year variations, which are due to synoptic scale, natural variations in the synoptic scale behavior. And so if you looked at the bottom right, the slide basically, the graph basically shows that if you look at that observed temperature record, the black line, and compare the model with that only takes into account the natural variations, the sun and volcanic eruptions, the model doesn't do a bad job for the first 50 years or so, but it can't match what kind of trend we've seen the last 50 years. Now, if you put in the increase in carbon dioxide and methane and nitrous oxide, the changes in ozone, changes in particles, et cetera, you get what's on the upper right-hand side, and you find that the model actually compares very well with what we've been observing. So if you're going to develop an alternative explanation for why the temperatures change, you've got to be able to explain why this would be wrong. And so far, there's nothing at all in the peer-reviewed literature indicating that this type of analysis is wrong. Well, you can actually do this. This is kind of a cartoonish version of a very detailed figure. But you can do this by looking over land versus over ocean. You can do it by looking at each of the continents. There's actually been analyses done at subcontinental scale, and you find the same thing. The only way you can explain the observed temperature record is by bringing in, particularly over the last 50 years, is by bringing in the effect of human activities and this increase in carbon dioxide, et cetera. Now, what are we observing in terms of the global change? Isn't just that average global temperature. If you look at the temperature distribution in detail, this is from the NASA Goddard Institute for Space Studies. If you just look back over time, say in the 1951 to 1980 period, you would have kind of a Gaussian curve. So some time periods you have much higher temperatures than others, other times much colder temperatures. Basically what we've seen since then, if you look at the three periods, 1981 to 1991, and then to 2001, and then to 2011, is that we're getting not only an increase in the average temperature, but we're seeing more high temperatures, more extreme temperatures. And I think that's much more worrisome, actually, than just the average change in temperature. It's the changes in severe events that I think are likely to have the most harm, both to humans and to the biosphere around us. If we turn to the 2009 assessment for the US, we can note that we saw many different things going on. The temperature's increasing in the US, and more precipitation coming as intense downpours, sea levels rising, we're seeing rapidly retreating glaciers. As I said, over 90% of the glaciers in the world, and essentially all but a few in the U.S. and those few are in Alaska. And even the scientists there say that those few that aren't decreasing are not decreasing because of climate change. And I'd have to go into some depth to tell you about that. Permafrost is melting in Alaska, and that's causing major damage there. We're seeing a longer growing season, which should help us with farming, but that's being counteracted a little bit by the increase in intense downpours and more likelihood of floods and droughts, both. And we'll talk a little bit more about that later. Well, since that assessment, we have new data analysis. The National Weather Service network has been carefully reanalyzed. The NOAA National Center for National Climate Data Center has totally looked at all the data, because there's been some concern, particularly in some of the blogs, that the instrument locations were affecting the trend. There really isn't an increase. How can you say that? That the But at the same time, we also know that some of the instrumentation changed. We also know that there was a timing change, changing the timing from late afternoon to early morning, and which would affect trends. And so the new analyses have re-examined that entire trend, and we have much more confidence now that the trends we're seeing really represent reality of what's going on. Well, this shows the observed trend over the U.S. Basically, over the last 50 years, we have seen a significant increase, going back to 1895, about 1.5 degrees Fahrenheit. And if you looked over the last 50 years, 1960 to 2009, the bottom right-hand side indicates that every part of the U.S. has seen an increase. And the size of the little circles there is how much of an increase. If you looked at the Midwest, we similarly see an increase, particularly over the last 50 years, with more of that increase appearing in winter and spring instead of summer and fall. The growing season across the U.S. has lengthened. As I mentioned earlier, that's continuing. In the Midwest, we've seen about a 9-day increase in the growing season over earlier in this century, over the last century. Well, one way of telling that there's a change occurring in our climate system is to look at the record breaking that is occurring. You know, more heat records are being broken than cold records. If there wasn't a changing climate, you'd expect it to be roughly the same, and that's what it was back in the 1950s. But if you compare that to the 2000s, we're now getting about 2 more record highs compared to record lows in the U.S. In 2011, that was 3 to 1, and in 2012 it was 10 to 1. It'd be interesting to see what's 2013, but so far I don't think we've been breaking a lot of records this year because of the cool in this region anyway, this part of the U.S. But I haven't seen an analysis overall. And again, we need to be looking at climatic timescales, we need to be looking at decade-plus analyses. Over the last 3 to 5 decades, we've seen an increasing trends for heat waves and a decreasing trend for cold waves across the U.S., particularly for heat waves in the western part of the U.S., not so much the eastern half. But a decreasing amount of cold waves everywhere. Doesn't mean we don't have cold waves, it just means we don't have as many as we used to. And you're looking at precipitation, generally the overall map of the U.S. shows the trend from the last 20 years compared to the previous 60, and generally there's an increasing trend over much of the U.S. Midwest has definitely seen an increase, has the Northeast, but other regions like the Southwest have seen very little change and even a decrease in some parts of that area. Well, the observations also show that more of the precipitation when it's coming is coming as larger events. Every part of the U.S. has seen an increase in the top 1% of its events. So if you go back over the past history and say, well, what over the last 50 years, what were the top 1%? So in the Midwest, that might be something like 4.5 inches of rain in a day. We've seen an increase in such events, a very significant increase, particularly here in the Midwest and in the Northeast. But all parts of the U.S. have seen an increase with more of the precipitation when it does rain coming as larger events. Another way of looking at this is some analysis done by one of my undergrad students working with me, looking at the data records, showing that we took the 1-year type event, the 5-year storm type event, or the 20-year event. So the 20-year event would mean like 1 in 20 years you would expect a precipitation that large. And in all cases over the last 50 years, we've seen an increase in such events with what was the 20-year event now being more like the 13-year event. So large precipitation is happening much, much more often than it did in the past. Certain parts of the U.S. are also seeing an increase in the amount of floods, particularly the Midwest and the Northeast. And other parts like the Southwest are seeing a decrease in the amount of floods. Likewise, in terms of looking at droughts, we don't overall see a significant change here in the Midwest, although we certainly had a very large drought last year. but long-term record doesn't show much of a change. But certainly in the western half of the U.S. and in the southeast, we've seen a significant increase in droughts over this last century. Well, another way of looking at whether the climate is changing, particularly severe weather, is to look at an analysis that NOAA has now been doing since 1980, where they look at what are the billion-dollar events. These are the events in the U.S. that are costing the American people at least $1 billion. And overall, we're seeing an increase in the number of such events. This doesn't have last year in it, but we had 14 such events in 2011, and we had 11 such events in 2012. So overall, since 1980, we have seen an increasing trend in such events. And then if you look at costs, Katrina was by far the most costly year, but even the last 2 years have been over $60 billion due to severe weather effects in the U.S. So it's definitely having an impact on our economy. Well, we know that from various scientific studies that there is a detectable human influence on the climate as a whole. More recent analyses are now looking at these kind of severe events. And when we do that, we find that the probability of such events have changed because the background atmosphere has changed. And in essence, the weather happening today is happening in the background of a changed climate. So if we look at the European heat wave of 2003 that resulted in 20,000 deaths in Europe and devastating effects on their crops and et cetera, the analyses indicate that that was much more likely because of the fact the background climate has changed. Moscow heat wave in 2010, very similarly. And analyses of the 2011 drought in Texas, Oklahoma indicate about a 3-to-1 more likelihood, factor 3 increased likelihood of that kind of large drought because of the fact the background climate has changed. Now, we could talk about the details of the meteorology, but basically that's what the studies are showing. Now, if we look at the projections for the future, we have a number of different types of analysis to try to say, well, how might humans continue to use fossil fuels or affect other emissions over this century? And so we have a range of things, ranging from we put policies into place very quickly to we continue down the path we're going, which would follow the actually higher than the highest scenario here right now. So there's two sets of scenarios for the future. The ones that were developed in around 2000 that were used in the last two international assessments, and then the new ones are the RCP scenarios. Basically, what they show is continued heavy use of reliance on fossil fuels means a very significant change in temperature across the U.S. Of 11 degrees or so by the end of the century. When you consider that an ice age is about a 20-degree cooling, that's a very significant fraction of change to show you what kind of changes that would mean. This will be a huge impact, and I'll show you a little bit more about that soon. The very lowest scenario here is the light blue one, RCP 2.6. That assumes we very soon move very rapidly away from the use of fossil fuels to alternatives. I don't think that one's really possible. I don't think we can possibly meet that. We could meet possibly, if we really decided to go for it, meet the RCP at 4.5. And that's still going to mean something in the order of about a 6-degree change, or as much as a 6-degree change. So the climate is going to continue to change. But we can prevent the very largest changes here by our actions, and we'll talk more about that later. Well, what does this mean for the U.S.? If you look at the U.S. as a whole, not every place is going to warm exactly the same, but nonetheless, we would expect here in the Midwest to see very, very significant changes, 9 to 10 degrees warmer. I don't know if I have the slide in here. I might. Well, I think I do. I'll hold off talking about 90-degree days and 100-degree days. Looking at precipitation, All scenarios basically show the same kind of basic behavior that we expect higher latitudes to have an increase in the amount of precipitation, and more that precipitation coming as larger events, and overall drying of the south and particularly the southwest. Basically, the dry get drier and the wet get wetter, in a very simple language. So here in the Midwest, we can expect an increase in precipitation in winter and spring, and perhaps a slight drying in the summer. But more of that precipitation in general, this is across the U.S., again, the analysis done by one of my students, comparing both with observations and then the new modeling studies, showing that not only have we seen an increase in precipitation coming as large events, but that's likely to continue with more and more of the precipitation coming as larger events. Another way of looking at this climate change, this is based on summer average temperatures and precipitation. The low scenario is what becomes the yellow there, and the high scenario is what becomes the red. Basically, if you follow the high scenario, the pathway we're on now, that and continue to use fossil fuels very heavily throughout the century, we're likely to have a climate much more like that of eastern Texas. Well, that's a climate where you have at least several weeks of 100-degree temperatures. Most of the summer is well above 90 degrees. Precipitation is maybe not all that different than what's in Texas right now. But basically, and this is for the summer, winters will be different than Texas. Don't expect you're going to get away with no snow. There'll still be snow in the winters. But it'll be maybe a little bit more like Pennsylvania in terms of what Illinois might look like in the winters. So that's a very different climate than we see now here in Illinois. You know, we're not used to those kind of summer temperatures and high humidity that goes along with it. So we're talking about very major changes in the climate. This particular graph has been shown a number of times before the U.S. Senate. Senator Dirksen Senator Dirksen. That's going back. Senator Durbin has shown it several times before the Senate. Well, the climate change we're seeing and are projected to see are likely to have a number of impacts on people and the environment around us. Concerns about health, concerns about species in natural areas and forests and coastal areas, and effects on water resources and agriculture and infrastructure, effects on our transportation systems, on our roads, on our energy systems. And lots of analyses are going on to try to understand those changes that are occurring already and what changes are likely to occur in the future. I'll just highlight a couple of things. But one thing to recognize is the temperature increases, and I apologize that this is in degrees centigrade, not Fahrenheit, but figure factor of 2 more for Fahrenheit, roughly. We're talking about very significant changes on those sectors as we get the increase in temperature. Sorry, I should turn this off. It's one of my students calling me. A little bit more detail. This is based on analysis we did for the city of Chicago that were published there in 2008, basically showing that we expect a significant increase in the number of days above 90 degrees, going to something like 70 to 80 in the high scenario, maybe 40 under the low scenario being equivalent to about that RCP 4.5. It was one of the other types of scenarios, but it's very similar. And a significant increase, almost a month of 100-degree days under the high scenario. And this is for Chicago. Probably be a little bit more so in this area. Well, one of the things we also did for the city of Chicago was look at the 1995 heat wave. That's the heat wave that resulted in over 800 deaths in the city. They're very concerned about heat waves, very extremely unusual events for the city. And they asked, well, how many of these kind of events are we likely to see in the future? So this just shows the analysis of, showing the a projected increase in such events as you go through the century, but by the end of the century, we were talking about 3 such events every year with the high scenario, and even with the low scenario, one of those kind of events every other year. So the city immediately put into place new adaptation measures, more green roofs, more trees in downtown, things that would help cool the city and help keep it cooler, and also better handling of emergencies and helping people when there is a heat wave that don't have air conditioning to get them into some place where they can survive that period. We're talking about a week-long event here where temperatures are in the 90s and hundreds for that week. Another concern of the city was heavy rainfall events. They were concerned that anytime you get more than 2.5 inches of rainfall, that the sewage water combines with the runoff, and you end up with a real mess in the streets in Chicago. If you've ever been up there during one of those events, it's rather amazing. What they often do is open up the gates to Lake Michigan and pour all that junk into the lake, which then results, if it's the wrong time of year, in algae bloom, and then they have to close the beaches, and the people get unhappy because the beaches are closed for health reasons. So they're in the process right now, as another adaptation measure, to totally redo how they handle this excess water, as well as trying to redo their sewage system in the city. Agriculture over the next few decades is not likely to see very significant effects, but in the longer term, I think it's going to see increasing challenges from heat stress, water stress, pests, diseases, and the weather extremes like I was talking about. More large events, and more floods, more droughts. We've been working closely with agriculture experts to look at these kind of issues. Generally, we expect less energy demand in the winter, so that's a good thing, but it's likely to be more than made up by the increased demand for air conditioning in the summer months. Well, what do? We got to meet this challenge. We can avoid the worst of these impacts. We can avoid the unmanageable, which means to avoid the worst of it, you can mitigate. But meanwhile, we're going to have to also learn to manage the unavoidable. The climate is likely to continue to increase. Temperature is likely to increase. The climate's likely to continue to change because of what we're doing with the emissions that are occurring. And we will have to learn to adapt. And some things we can adapt well to, and others we can't. There's been a number of economic analysis to try to say, well, how could we change this picture for the future? And this just shows kind of a starting point of, it's kind of old now, starting in 2010, of trying to start to do something about it to avoid the very top level of that change, and this is in terms of tons of carbon out of the US. And there's this method called wedges, where you look at a number of different possible ways of reducing the emissions. Some of that is through being more efficient in how we handle energy, and some of it is through actual mitigation processes and changing our energy and transportation systems. And so we can reduce emissions a great deal, but we have to, of course, desire to. A number of economic analysis, published economic analysis and peer-reviewed literature, have shown that the benefits of strong early action on climate change far outweigh the cost. But nonetheless, since we're not seeing the large changes yet that we expect to see in the future, it's been difficult to get Congress to actually move in terms of trying to prevent some of those. Our future really depends on how we act to limit climate change. Adaptation's not a choice. Our choice is whether to adapt proactively or respond to the consequences of the changes occurring around us. Adaptation requires a paradigm shift, focusing on managing risk. And risk management is really what it's all about. We can draw, as American people, we can draw on our long history of responding to changing conditions in facing the challenges of climate change. In conclusion, climate is changing in the U.S., largely as a result of human activities. These changes are likely to continue. How How large they are, it really depends on us and the others in the world around us, because we're all in this together. The growing season is getting longer and is likely to continue to get longer. Certain types of extreme weather events are becoming more common, and those trends are likely to continue. More precipitation coming as larger events, heat waves generally increasing, likely to become longer and more severe. Cold waves are becoming less common, increasing risk of floods and droughts in some regions of the U.S. Sea level, I haven't really talked about sea level. Sea level is increasing, likely to increase by 1 to 4 feet over this century based on the National Climate Assessment. And these changes are already significantly affecting the U.S. and likely to continue. So I thank you, and I'm happy to address any questions you might have.